All right, so we've learned that confidence intervals based on small samples from normally distributed populations are calculated with the t-statistic. Let's check a similar example to the one we saw earlier. You are an aspiring data scientist and are wondering how much the mean data scientist salary is. This time, though, you do not have the population variance. In fact, you have a sample of only 9 compensations you found on Glassdoor and have summarized the information in the following table. Okay, we've already calculated the sample mean and standard error, which are $92,533, $4,644, respectively. Good, but we don't have one key piece of information, the population variance. No problem. As the good statisticians that we are, we will use the student's t-distribution. Here's the formula that allows us to find a confidence interval for the mean of a population with an unknown variance. Let's compare it with the formula we use when the variance is known. There are 2 key differences. First, instead of a z-statistic, we have a t-statistic. And second, instead of population standard deviation, we have sample standard deviation. Otherwise, everything is the same. So, it shouldn't be that difficult to remember. The logic behind constructing confidence intervals in both cases is the same. The only 2 inputs that change are the statistic at hand and the standard deviation. When population variance is known, population standard deviation goes with the z-statistic. When population variance is unknown, sample standard deviation goes with the t-statistic. All right, so we have the sample mean, standard deviation, and sample size. All we have to do is find the t-statistic. We will be able to obtain the t-statistic from the t-table. First, we need to specify the degrees of freedom. For the student's t-distribution, there are n-1 degrees of freedom. Our sample consists of 9 observations, so we have 8 degrees of freedom. Second, we have to find alpha divided by 2. Once again, this depends on the confidence level that we want to obtain. In this example, we are going to use a confidence level of 95%. This means that alpha is equal to 5%. Therefore, half of alpha would be 2.5%. You can now see that the associated t-statistic is 2.31. Great! Note that some t-tables you will find in books or online, like this one, have a CI row. The abbreviation stands for confidence interval. Instead of finding alpha, we can just check the 95% confidence interval and get the same result. Easy. Okay. We have all the information needed, so we just plug in the numbers. What we get is a confidence interval from $81,806 to $103,261. Let's compare this result to the result for the confidence interval with known population. We got a 95% confidence interval that was between $94,833 and $105,568. You can clearly note that when we know the population variance, we get a narrower confidence interval. When we do not know the population variance, there is a higher uncertainty that is reflected by wider boundaries for our interval. Makes sense, doesn't it? So, what we learned today is that even when we do not know the population variance, we can still make predictions, but they will be less accurate. Furthermore, the proper statistic for estimating the confidence interval when the population variance is unknown is the t-statistic and not the z-statistic. All right, great. Thanks for watching.